Hey guys, this is Nona. So in this video, we're going to be talking about cardiac action potentials. This is part one, so I'm just going to go over the non-pacemaker action potentials, and then in part two, we'll go over the pacemaker action potentials. So the heart's main job is to pump blood to the rest of the body, and it does so by contracting. So the heart's made up of cardiac myocytes, which are specialized muscle cells, and remember that they're connected by these gap junctions. So this is important because the gap junctions allow for the action potential to travel from cell to cell, and this allows for the action potential to propagate and cause a nice synchronized contraction of the heart. These muscle cells contract when they are stimulated by electrical activity, or in other words, an action potential. So let's go through the action potential step by step. So up here, I'm going to draw the graph that we're going to fill in. So on the x-axis, we have time, and this is on the scale of milliseconds. And then on the y-axis, we're going to graph voltage, and this is going to be in millivolts. I'm going to extend this a little bit. So down here, we'll start at negative 100. Up here, I'll have it at 0, and about halfway in between, this can be negative 50. And also on this graph, I'm going to sketch in a line that runs here at around negative 70. And this is going to be what's called the threshold potential. You can see my inability to draw straight lines. Okay. So down here, we can track what is going on in the cell itself through time. So this is the cell membrane that I'm drawing. So this is a phospholipid bilayer. And we'll say that this is the outside of the cell. And then this can be the inside. And how this is going to work is this is also going to be tracking through time. So whatever is happening here should correlate with whatever I draw up here. And throughout time, we want to keep track of what phase we're in and what the voltage is, right? So there's 5 main phases to a non-pacemaker action potential, and they're labeled phases 0 through 4. So we're going to go a little bit backwards. We're actually going to start at phase 4. And at phase 4, the cell is at its resting potential. So what does that mean? At rest, the ion that's going to predominate on the inside of the cell is going to be potassium. And then on the outside of the cell, we've got sodium and also calcium. So that's kind of the steady state of things. And just at rest, the cell is very permeable to potassium. So potassium is just going to be able to leave the cell, and it does so quite easily. So because of that, the resting potential sits at about negative 90 millivolts. So notice it's negative on the inside relative to the outside. And when we go through this action potential, it's basically a brief reversal of this polarity in membrane. So that's phase 4. So we can graph it up here on the graph. So negative 90 is probably about here, and the cell's at rest, right? So it's throughout time, it's just going to stay flat like this. Okay, so we can move on to phase 0. So recall that these cells are all connected by gap junctions. So from a neighboring cell, usually some positive charge flows over from sodium, calcium, so this comes over from a neighboring cell, and it flows freely into our cell here. So you can imagine if more positive charge is coming in, this negative 90 is going to become more and more positive, or another way to say it is it's going to become less negative. So let's say it becomes less negative to about negative 70 millivolts. So this happens fairly quickly, so it's going to be a pretty steep slope. Then once it hits negative 70, something interesting happens. So recall that all of these ions have what's called a voltage-gated channel, and voltage-gated ion channels are specific to a specific ion, and they open at a particular voltage, and they also close at a particular voltage. So the sodium's voltage-gated ion channel is going to open at -70, so that's why it's called the threshold potential. So let me just draw this in. So recall that there's like a ton of sodium outside. So there's a huge gradient. And once this opens, sodium will just come rushing in. And this is a fairly fast process. Sometimes you'll hear these channels be referred to as the fast sodium channels. So let me graph this. So it's going to basically shoot up the membrane potential to even past 0. So maybe let's just say like plus 20. Okay. And then we can get to phase 1. So once we're at the end of phase 0, the sodium channels open quickly, but they also close just as quickly once you get to kind of a more positive membrane potential. And then that begins phase 1. So phase 1, so just like how sodium had a voltage-gated ion channel, so does potassium. And remember, potassium predominantly lives inside the cell at rest. So there's going to be a ton of potassium here, and it's going to want to leave. Draw that here. So just to recap, we had sodium coming in that made it positive. Now we have positive charge from the potassium leaving. So this is going to cause the membrane potential to go more negative, right? So that's why we see this initial dip. Should probably make this bigger. So this is phase 1, this is phase 0, and this is phase 4. So let's talk about phase 2 now. So in addition to the potassium leaving, something interesting also happens. So we haven't talked about calcium yet, right? So calcium predominantly is going to be on the outside of the cell. So calcium also has its own channels. And calcium, sometimes you hear them be called L-type calcium channels. These are also called slow calcium channels because they slowly open, they slowly close. So calcium channels are going to open and calcium is going to want to come inside because of the gradient. And at the same time, potassium is also trying to leave. So let's think about this. We've got positive charge trying to leave, but then we also have positive charge trying to come inside. So that's what causes this plateau period. So notice this gives the cardiac action potential its distinctive shape. That's going to be called phase 2. And then the last phase is phase 3. So what happens is eventually the slow type calcium channels eventually close, and all we have left is the potassium channels open, and potassium will keep leaving without the calcium coming in. So we just have positive charge leaving, so that this membrane potential is going to go back to being negative. And then at this point, the cell is going to reset its gradients with the sodium-potassium pumps and calcium pumps so that the cell can be ready for another action potential. And we start over, and this is phase 4. Okay, so let's review. This is the cardiac action potential, right, the non-pacer one. So we start at a voltage of about -90, and we have influx from sodium, right? This is from the neighboring cells via the gap junctions. And then this causes the membrane potential to go up until this threshold potential about -70, in which case the voltage-gated ion channels open. So then these open, sodium comes rushing in. So this is a relatively steep slope. It's also called rapid depolarization. And then the sodium channels also close. And then they didn't draw a huge phase 1, so this is phase 0, this is phase 4. But this will be their phase 1 when it kind of dips down a little bit when just the potassium is leaving. But then the slow calcium channels open. So you have calcium coming in but potassium leaving, so that's why you have a plateau, and that's phase 2. And then the slow calcium channels close, and then you just have the potassium channels open, so that's why we get this repolarization stage, or stage 3. And then finally the potassium channels close, and then we reset, and we're back at phase 4. All right, that's it. Thanks for listening.